welcome back to the Science Pillow. Wherever you are right now, whether you are lying in a warm bed with the lights already dimmed, resting your head on a pillow while the quiet world outside settles into its nighttime rhythms, or perhaps sitting somewhere soft and still with a cup of something warm, I want you to know that you have found exactly the right place to be. This channel exists for moments like this one. Moments when the day is finally behind you, when the noise and the demands and the long list of things that needed doing have finally, mercifully, released their grip on your attention. This is your time now. Time to let your mind wander somewhere vast and beautiful and strangely peaceful. Tonight, we are going to travel somewhere extraordinary. We are going to follow a comet. Not just any comet, but one unlike anything that has ever passed through our corner of the universe in all of recorded human history. A comet that arrived without warning, that came from so impossibly far away that its home star may no longer exist, that carries chemical secrets from the early days of the galaxy itself, and that quietly slipped through our solar system in the year 2025. Observed by dozens of the most powerful telescopes human beings have ever built, before departing once more into the dark between the stars, never to return. Its name is 3I/Atlas, and its story is one of the most genuinely remarkable things science has encountered in a very long time. Now, before we go any further, if you are new here, this is what the Science Pillow does. We take the real science, the verified, peer-reviewed, confirmed science, and we tell it to you slowly, gently, with all the wonder it deserves, in a way that is designed to help you relax, to drift, to find that particular kind of restfulness that comes when your mind is gently occupied by something fascinating rather than spinning in anxious circles about the day. There will be nothing rushed here. There will be no urgency, just the quiet, extraordinary truth of the universe, unfolding at whatever pace suits you. So, if you are comfortable, take one long, slow breath with me. Feel the weight of your body settle. Let your shoulders drop. Let your jaw soften. Whatever you are carrying today, you can set it down now, right here, at the beginning of this story. The universe is very, very old, and it has been getting along just fine without any of us worrying about it. Tonight you get to simply watch it, the way you might watch stars through a window. And on that note, let us begin. If you are enjoying tonight's journey, and you find that the Science Pillow helps you rest, please consider leaving a like on this video. It genuinely helps more people discover this channel, which means more curious minds get the rest they deserve. And if you have not yet subscribed, I would gently encourage you to do so. There are many more journeys like this one waiting for you, covering everything from the deepest reaches of the cosmos to the quiet mysteries of the natural world. Now, let us find our comet, the night sky, and the long human habit of looking up. There is something deeply ancient about what we are going to do tonight. Long before there were telescopes, long before there were cities or writing or any of the complicated machinery of civilization, human beings looked up. They sat around fires, or they lay in open fields beneath skies darker than almost anyone alive today has ever seen. And they watched the heavens with a combination of awe and curiosity that seems to be simply part of what we are. The night sky was the first great mystery, the first unfathomable question, the first thing that made people feel simultaneously very small and somehow very significant. Comets, in particular, have always held a special place in that ancient relationship between human beings and the sky. They appear without warning. They hang in the darkness like slow-moving smears of light, their tails stretching across the sky for weeks, sometimes months, before fading just as mysteriously as they arrived. Ancient observers, who had no framework for what comets actually were, tended to interpret them as messages, as omens of change, of upheaval, of things that were about to happen whether you wanted them to or not. The comet that appeared before the death of Julius Caesar in 44 BC was interpreted by the Roman people as the soul of Caesar ascending to the heavens. The appearance of Halley's comet in 1066 was stitched into the Bayeux tapestry, depicted as an object of terror and wonder, hanging over the heads of the frightened English who watched the Norman conquest unfold beneath it. We understand now what comets actually are. They are icy bodies, remnants of the formation of planetary systems, leftovers from the great cloud of gas and dust that swirled and condensed into whatever star system produced them. They are, in a sense, the discarded material of world building, the stuff that never quite made it into a planet. Some of them have been wandering the outer edges of our own solar system since the sun was young, in the vast, cold, distant region astronomers call the Oort cloud. Billions of objects drift in long, slow orbits, occasionally nudged inward by gravitational interactions with passing stars or with each other, falling toward the sun in long, curving arcs that bring them briefly into the warmth and light of the inner solar system before sweeping them back out into the dark. When a comet approaches the sun, something magical happens. The heat begins to reach the icy nucleus. Gases that have been frozen solid for millions or billions of years suddenly sublimate. They transition directly from ice into gas, carrying dust with them as they escape from the comet's surface. This outgassing creates the coma, that glowing cloud of material that surrounds the nucleus, and as solar wind pushes against that cloud, it creates the tail, sometimes two tails, one made of dust and one of ionized gas, both pointing away from the sun regardless of which direction the comet is actually traveling. Comets are, in this sense, little time capsules. They preserve material from the earliest moments of their home planetary system, holding it frozen and unchanged until that one great plunge through the warmth changes everything. For most of human history, the comets we saw were all our comets, objects that formed in our own solar system billions of years ago, in the same vast cloud of gas that gave birth to the sun and the earth and the other planets. The idea that a comet might arrive from somewhere else entirely, from another star, another solar system, another corner of the galaxy, was just that, an idea, a theoretical possibility that astronomers had considered but never been able to observe. They had models suggesting that planetary systems must eject enormous numbers of small objects during their formation. Gravitational interactions between young planets and comets or asteroids can fling those smaller bodies at tremendous speeds, casting them outward past the edge of their home system into the cold, dark space between the stars. If this happened in our solar system, and there is good reason to think it has happened throughout our solar system's history on a massive scale, then it must be happening around other stars too. And if it is happening around other stars, then interstellar space must be thick with these wandering objects. Objects from somewhere else, drifting through the galaxy for millions or billions of years, occasionally stumbling through the neighborhood of some other star. The question was whether we would ever actually see one. And then, in October 2017, we did. And the universe has not quite looked the same since. The first visitors, Oumuamua and Borisov. The story of 3I/Atlas properly begins not in 2025, but 8 years earlier, on the night of October 19, 2017. A telescope called Pan-STARRS in Hawaii, scanning the sky as part of a routine survey, picked up something strange. A faint, fast-moving object that appeared and disappeared in the survey data. When astronomers computed its orbit from the available observations, they found something that had never been found before in the history of astronomical observation. The orbit was hyperbolic, and not just mildly hyperbolic, not in a way that could be attributed to some unusual gravitational interaction within our solar system, but decisively, unmistakably hyperbolic. This object was moving too fast to be bound by the sun's gravity. It was not going around the sun. It was passing through. The object was given the name 1I/Oumuamua, where the 1I stands for the first interstellar object, and Oumuamua itself is a Hawaiian word meaning, roughly, a messenger from afar arriving first. And it was strange. Oumuamua, profoundly strange, unlike anything astronomers had expected a visiting interstellar object to look like. It showed no coma, no tail, no outgassing of any kind, all things you would expect from a comet approaching a star. Its shape, deduced from the way its brightness varied as it tumbled, seemed to be extremely elongated, possibly a flat, disc-like object or a long, thin one, with proportions quite unlike typical solar system objects. And then there was the acceleration. As Oumuamua moved away from the sun, it accelerated slightly more than gravity alone could account for. In a comet, this non-gravitational acceleration would be explained by the force of gas being ejected from the surface. Essentially, the comet pushing itself like a rocket. But there was no gas. There was no coma. There was no tail. And the acceleration continued anyway. Oumuamua sparked enormous debate. Various explanations were proposed. The most widely accepted scientific hypothesis is that it might be a fragment of a nitrogen-rich object, similar to Pluto, where the slow sublimation of nitrogen, a gas so transparent it would be essentially invisible even to our best instruments at that distance, provided the observed push without creating a detectable coma. Others proposed that it might be a naturally produced hydrogen iceberg. A small number of researchers, most vocally the Harvard astrophysicist Avi Loeb, proposed that the object might be an artifact of extraterrestrial technology, something constructed rather than natural. The mainstream scientific community found this explanation unsupported by the evidence, but the debate illustrated just how unusual Oumuamua was. Whatever it was unlike anything we had ever seen before, and it left our solar system without giving us enough time or observational access to resolve the mystery. Then came the second visitor. On August 30th, 2019, an amateur astronomer in Crimea named Gennady Borisov, who had built his own telescope, spotted a fuzzy, slow-moving object in the sky. When professional astronomers followed up on his report and computed the orbit, they found it, too, was hyperbolic. Another interstellar visitor. This one received the designation 2I/Borisov, in honor of its discoverer, and from the very beginning it behaved in a far more familiar way than Oumuamua had. It had a coma. It had a tail. It outgassed in the way comets do. When spectroscopic observations were made of its coma, astronomers found water vapor, carbon monoxide, oxygen, and other molecules that were, broadly speaking, similar to what you would find in a comet from our own Oort cloud. There was one notable difference. The carbon monoxide abundance was higher than typical solar system comets, suggesting that Borisov had formed in the cold outer reaches of its home star system. But overall, 2I/Borisov looked and behaved more or less like a comet, just a comet from somewhere else. Borisov, unlike Oumuamua, was discovered while still relatively far from the Sun, giving astronomers months to observe it. They tracked it through Perihelion, its closest approach to the Sun, and watched as it subsequently began to show signs of fragmentation, as the heat and stress of perihelion passage caused small pieces to break off from its nucleus. The nucleus itself was estimated at somewhere between 0.4 and 1 kilometer across. After perihelion, it faded back into the darkness, departing our solar system on its hyperbolic trajectory, carrying material from some other star's planetary disk on its endless journey through the interstellar void. 2 interstellar objects in 2 years. The astronomical community was buzzing. If 2 had been detected in such a short span, the population of these objects throughout the galaxy must be genuinely enormous. Estimates were made. Some researchers calculated that at any given moment, there could be thousands of interstellar objects within the orbit of Neptune, simply too small or too faint or moving in the wrong direction for our current instruments to detect. The Vera C. Rubin Observatory, a powerful new instrument then under construction in Chile, was expected to change this dramatically when it came online. Its massive 8.4-meter mirror and 3.2 gigapixel camera, scanning the entire southern sky every few nights, would be capable of detecting far fainter and more distant objects than anything before it. For nearly 6 years after Borisov, the sky remained quiet in terms of interstellar visitors. Astronomers waited. Survey telescopes kept scanning. And then, on the 1st of July, 2025, the universe sent us its third message from beyond the solar system. And this one was unlike either of what had come before. Discovery, July 1st, 2025. The Asteroid Terrestrial Impact Last Alert System, ATLAS, is not a single telescope but a network of them, spread across multiple sites around the world. Its original purpose is exactly what the name suggests: to provide early warning of asteroids that might be on a collision course with Earth. The system works by repeatedly scanning the sky and alerting astronomers when something appears to be moving in an unexpected way. It is, in a sense, a sky-wide alarm system for incoming objects. On July 1st, 2025, one of the ATLAS telescopes located in Rio Hurtado, Chile, detected a faint object moving through the sky and reported its observations to the Minor Planet Center, the international clearinghouse for data about small bodies in the solar system. In the first hours after the report, the object was given the temporary designation A11PL3Z, just a string of letters and numbers to keep track of it while its orbit was being calculated. At first, the A's initial observations were somewhat ambiguous. The early data was consistent with an object that might come close to Earth's orbit, which is why the Minor Planet Center temporarily listed it on the Near-Earth Object Confirmation page, a list of objects that might pose a risk, pending further observation to clarify their orbits. Astronomers around the world, both professional and amateur, began following up with their own telescopes. Within hours, the picture started to clarify, and the clarification was astonishing. The orbit was not just unusual, it was hyperbolic to a degree that had never before been recorded for any natural object. As observations accumulated and the orbital solution became more refined, the eccentricity of the orbit, the number that describes how stretched or curved a path is, where an eccentricity of exactly 1 means a parabola and greater than 1 means a hyperbola, meaning the object is not gravitationally bound to the Sun, came out at 6.141. To put that in context, Oumuamua had an eccentricity of 1.2. Borisov had an eccentricity of 3.4. This new object, with an eccentricity of over 6, had an orbit so wildly open and stretched that it appeared, as observers noted, almost perfectly straight rather than curved. It was not going around the Sun. It was barely even deflected by the Sun. It was going through. Astronomers scrambled to search their archival data for earlier observations that might help refine the orbit. The Zwicky Transient Facility at Palomar Observatory in California found pre-discovery observations going back to June 28th and 29th. Multiple Atlas telescopes had their own pre-discovery images going back to June 5th. A researcher at the Weizmann Astrophysical Observatory in Israel found an observation from May 21st. The earliest confirmed observations from NASA's Transiting Exoplanet Survey satellite suggested the comet may have been displaying cometary activity, the earliest stirrings of its coma, as far back as May 7th, when it was still 6.4 astronomical units from the Sun, roughly the distance of Jupiter. One of the reasons the object was not discovered earlier was particularly interesting. It had been approaching from the direction of the constellation Sagittarius, which places it against the extraordinarily dense backdrop of the galactic center, a region of sky so crowded with stars that a small moving object can easily be lost in the visual noise. Once that directional geometry changed as the comet moved, it became detectable. Amateur astronomer Sam Dean noted this and suggested it likely explained why the discovery was delayed. By the time the Minor Planet Center formally announced the discovery on July 2, 2025, they had collected 122 separate observations from 31 different observatories. The object received the designation 3I/Atlas, third interstellar discovered by Atlas. It also received the non-periodic comet designation C/2025 N1. Observations by David Jewett and Jane Liu, using the Nordic Optical Telescope on that same day, confirmed that the object was clearly active. It had a coma. It was a comet. The third known interstellar object and the second known interstellar comet had arrived. By the time official confirmation was announced, the comet was already within the orbit of Jupiter, approximately 670 million kilometers from the Sun, about 4.5 times the Earth-Sun distance. It had been traveling toward us for who knows how long, and it was moving fast. At the moment of discovery, 3I/Atlas was traveling at approximately 137,000 miles per hour, 221,000 kilometers per hour, relative to the Sun. This was its speed at that distance, already somewhat slowed from its true interstellar velocity by the Sun's gravity beginning to pull it inward. Its true hyperbolic excess velocity, the speed at which it arrived from interstellar space before the Sun's gravity began influencing it, was approximately 58 kilometers per second, or about 130,000 miles per hour. For comparison, Oumuamua's hyperbolic excess velocity was 26 kilometers per second, and Borisov's was 32 kilometers per second. 3I/Atlas was traveling nearly twice as fast as either of its interstellar predecessors. It was the fastest interstellar object ever recorded by human instruments. Reading the orbit. What the numbers tell us. Orbital mechanics is one of those areas of science where a handful of numbers can tell an extraordinary story. When astronomers look at the orbit of 3I/Atlas, at its eccentricity of 6.141, at its inclination of 175 degrees, at its hyperbolic excess velocity of 58 kilometers per second, each of those numbers opens up like a door into deep time and deep space, revealing something about where this object came from and what its existence means. Let us start with the eccentricity. Every orbit can be described by this single number. A circle has an eccentricity of 0. The Earth's orbit around the Sun has an eccentricity of about 0.017, almost perfectly circular, with just a slight elongation. Comets from the Oort cloud, the vast shell of icy bodies surrounding our solar system at enormous distances, often have eccentricities very close to 1, meaning their orbits are extremely elongated ellipses that take them out to extraordinary distances before they fall back in. An eccentricity of exactly 1 would mean a parabolic orbit, and anything greater than 1 means the object is simply not bound to the Sun at all. It will pass through once, reach its closest point, and then leave forever, never to return. The higher the eccentricity above 1, the more the orbit departs from anything that could have originated within the solar system's gravitational influence. 3. I/Atlas's eccentricity of 6.141 is, to put it simply, extreme. It is not just slightly above 1. It is not modestly hyperbolic. It is so dramatically hyperbolic that its path through the solar system appeared nearly linear to astronomers making their measurements. The object was not captured by the Sun's gravity, not even slightly deflected from what was essentially a straight-line trajectory through our neighborhood. It came in from the direction of Sagittarius, the direction of the galactic center, passed through the inner solar system, came closest to the Sun on October 29, 2025, at a distance of about 1.36 astronomical units, roughly between the orbits of Earth and Mars, and then departed outbound. The inclination of 175 degrees is another remarkable number. An inclination of 0 degrees would mean the orbit is perfectly aligned with the ecliptic plane, the flat disk in which the planets orbit the Sun, and moving in the same direction as the planets. An inclination of 180 degrees would mean moving in the same plane but in exactly the opposite direction to the planets. At 175 degrees, 3I/Atlas was moving almost exactly against the direction of planetary motion, a retrograde orbit, tilted only 5 degrees off the plane of the solar system. This retrograde motion in a nearly ecliptic-aligned orbit is deeply unusual for an interstellar visitor, which would be expected to arrive from a more or less random direction. The alignment with the ecliptic plane sparked some initial speculation and debate that we will return to later. Now, let us think about what the speed tells us about the object's history. The hyperbolic excess velocity of 58 kilometers per second represents the speed 3I/Atlas was traveling through interstellar space before the Sun's gravity began affecting it. This is fast, but not implausibly so. Icy bodies ejected from planetary systems during the chaotic early phases of those systems' formation can achieve velocities in this range through gravitational interactions with massive planets. The diversity in speeds among the 3 known interstellar objects, 26, 32, and 58 kilometers per second, suggests they experienced different ejection histories in their home planetary systems. But 58 kilometers per second is also fast enough to tell us something about how long 3I/Atlas has been wandering. As an object travels through the galaxy, it experiences gravitational influences from the stars it passes near, from the overall gravitational potential of the galactic disk, from giant molecular clouds. These interactions tend to gradually increase the object's velocity relative to the local standard of rest, the average motion of stars in the Sun's neighborhood. The higher the velocity, the longer, statistically speaking, the object has been subject to these random gravitational nudges. When researchers tracked 3I/Atlas's trajectory back in time using the known gravitational potential of the Milky Way, the calculations pointed to an origin in the galactic thick disk, a population of older, lower metallicity stars that formed in the early days of the galaxy. Estimates of the comet's age ranged from about 7.6 to 14 billion years, with a median estimate from one Bayesian analysis pointing to around 9.6 billion years. For comparison, our solar system is 4.6 billion years old. The universe itself is 13.8 billion years old. If these age estimates are correct, then 3I/Atlas may be the oldest comet ever directly observed by human beings. It formed in Inhabit, planetary system around a star that might have lived out its entire stellar life and died billions of years before our Sun even ignited. It was ejected from that system at some point in its history, most likely through a gravitational interaction with a giant planet, the kind of violent billiards that characterize the formation and early evolution of planetary systems. And then it wandered. For perhaps 9 or 10 billion years, it drifted through the darkness between the stars, carrying frozen within it the chemical signature of a world that no longer exists. Until, in the summer of 2025, it happened to pass close enough to our Sun to warm up, and, in warming up, to speak. The comet itself, what it looks like, and what it is made of. One of the most extraordinary aspects of 3I/Atlas was the sheer breadth of instruments that turned to observe it. Within days of its discovery, telescopes from around the world, and from spacecraft scattered across the solar system, began collecting data. Hubble Space Telescope, James Webb Space Telescope, the Very Large Telescope in Chile, the Gran Telescopio Canarias in Spain, Spirex, TESS, the Nordic Optical Telescope, the Subaru Telescope, the Allen Telescope Array, the Green Bank Telescope, the Meerkat Array in South Africa. And, in an unprecedented mobilization of planetary resources, a fleet of spacecraft already working throughout the solar system. Parker Solar Probe, Europa Clipper, NASA's Psyche spacecraft, the Lucy mission, the Punch mission, the Maven spacecraft at Mars, the Mars Reconnaissance Orbiter, the ExoMars Trace Gas Orbiter, all turned their instruments in one way or another toward this single remarkable object. The first Hubble observations, made on July 21, 2025, revealed a striking image. The comet displayed what NASA described as a teardrop-shaped cocoon of dust surrounding its nucleus, the characteristic shape of a coma being pushed back by the solar wind, creating a rounded sunward side and a stretched anti-solar tail. The background stars in the Hubble image appeared as streaks because Hubble was tracking the fast-moving comet rather than holding still against the stellar background. In subsequent Hubble observations through August, astronomers were able to use the detailed data to constrain the size of the nucleus. Their estimates placed it somewhere between 440 meters, about the length of 4 American football fields, and 5.6 kilometers across. Later, refinements from multiple instruments suggested the nucleus was likely under 1 kilometer in diameter, meaning it is actually rather small, smaller than many solar system comets. This was an important finding, because initial ground-based estimates, based on the comet's overall brightness, had suggested it might be as large as 10 to 20 kilometers across, potentially the largest interstellar object ever detected. The resolution of this discrepancy came from understanding how active 3I/Atlas was. When you observe a comet from a distance, what you often see is not the nucleus itself, but the much larger coma, the cloud of gas and dust surrounding the nucleus. A smaller nucleus that is highly active, producing large amounts of gas and dust, can appear just as bright as a larger, less active nucleus. The Hubble observations revealed that what ground-based telescopes were seeing was primarily the coma and its dust, not the nucleus directly. The comet was behaving like a highly active, energetic producer of material, even though its solid body was relatively modest in size. Photometric observations established that 3I/Atlas had a spin period of approximately 16.16 hours, the time it takes to rotate once on its axis. This is consistent with what you would find for an active solar system comet, and suggests the nucleus is behaving dynamically in a way that tracks with our understanding of cometary physics, even from an entirely different star system. The coma itself, at its most visible extent, was approximately 26,400 by 24,700 kilometers across, roughly twice the diameter of Earth, and the color of the coma was reddish, a characteristic that planetary scientists associate with organic rich materials, specifically compounds called tholins, which are complex organic molecules formed when simpler chemicals are processed by radiation over long timescales. This reddish color is similar to what was observed in 2I/Borisov, and to the colors of certain classes of asteroids and outer solar system bodies in our own solar system. But it was the James Webb Space Telescope's observations that produced the most startling revelations about what 3I/Atlas is actually made of. On August 6, 2025, JWST pointed its near-infrared spectrograph at the comet when it was still 3.32 astronomical units from the Sun, further out than Mars, and made measurements across the wavelength range from 0.6 to 5.3 micrometers. What it found in the coma was deeply unusual. The dominant gas in the coma was not water vapor, as you would expect from a typical solar system comet at that distance. It was carbon dioxide. The ratio of carbon dioxide to water vapor in 3I/Atlas's coma came out at approximately 7.6 to 1. In solar system comets, you might typically see a CO2 to water ratio of around 1 to a few. Carbon dioxide is present, but water is usually the main driver of cometary activity. For 3I/Atlas, the ratio was inverted and extreme. It ranked among the highest CO2 to water ratios ever recorded in a comet, sitting 4.5 standard deviations above the trend observed for long-period and Jupiter family comets from our own solar system. Carbon dioxide sublimates, turns from solid to gas, at much colder temperatures than water, which means a comet rich in CO2 can become active much further from its star than a water-dominated comet would. This matched what observers had seen with 3I/Atlas. It was already visibly active at greater distances from the Sun than would be expected if water were the primary driver. The JWST team, led by Martin Kordener, of NASA's Goddard Space Flight Center, offered two main explanations for the anomalous CO2 abundance. One possibility is that the ices within 3I/Atlas were exposed to much higher levels of cosmic radiation during their long interstellar journey than typical solar system comets experience. Radiation can alter the chemical composition of ices over time, potentially depleting water relative to CO2. The other possibility is that 3I/Atlas formed relatively close to the CO2 frost line, the boundary around its parent star beyond which temperatures are cold enough for CO2 to condense into solid form, giving it an inherently CO2-rich composition from the moment of its formation. In either case, the implication is that this comet experienced a chemistry and a formation environment that was meaningfully different from what produces typical solar system comets. The building blocks of at least one other planetary system, it seems, were not identical to our own. SphereX, NASA's infrared survey satellite, also observed 3I/Atlas and confirmed the high CO2 content, though it lacked the sensitivity to detect the water and carbon monoxide that JWST found. The Very Large Telescope made additional spectroscopic detections of cyanide gas and atomic nickel vapor in the coma. The nickel detection was not particularly surprising. Nickel has been detected in other comets, including 2I/Borisov, but the absence of iron was. Nickel and iron are typically found in roughly equal proportions when they outgas from comets, because they tend to originate from the same class of minerals. In 3I/Atlas, only nickel was detected, with no detectable iron. Another small puzzle to add to the growing collection. In late November and early December 2025, X-ray telescopes XRISM, operated by JAXA, the Japan Aerospace Exploration Agency, and XMM Newton, an ESA mission, detected a diffuse X-ray glow extending about 400,000 kilometers around the nucleus. This made 3I/Atlas the first interstellar comet ever observed in X-ray light. Another first for an object that seemed determined to set records. The X-rays are produced when highly charged solar wind particles interact with the gas in the comet's coma, a process that has been observed in solar system comets but had never previously been measured in an interstellar visitor. In November 2025, observations from the Gemini North Telescope revealed that the comet had changed color, from reddish to a greenish hue. The green color comes from diatomic carbon molecules, C2, which glow in the visible spectrum when energized by sunlight. This color change as the comet approached and then receded from the sun reflects the evolving chemistry of its coma, as different volatiles became active at different temperatures. Where did it come from? Tracing the path back through the galaxy. One of the first questions anyone asks when an interstellar object arrives is the obvious one. Where did it come from? And the answer, in the case of 3I/Atlas, is simultaneously more and less satisfying than you might hope. Astronomers can trace the trajectory back in time with considerable precision. They know where the comet was, and they know what direction it was traveling, and they can run the orbital calculations backward using models of the Milky Way's gravitational field. What they cannot do, at least not with current technology, is trace the path all the way back to a specific star and say definitively that this comet was born in that system. The galaxy is large, the stars are many, and billions of years is a very long time during which many gravitational nudges can send an object wandering across paths that become impossible to reconstruct with certainty. What the orbital backtracing does tell us is the galactic population from which 3I/Atlas most likely originated. When you break down the comet's velocity into its components in the galactic coordinate system, how fast it is moving toward or away from the galactic center, the U velocity, how fast it is moving in the direction of galactic rotation, the V velocity, and how fast it is moving perpendicular to the galactic plane, the W velocity. You get a picture of its membership in galactic stellar populations. The vertical component of 3I/Atlas's velocity, the W velocity, is relatively high compared to nearby stars and compared to the other two interstellar objects. This high vertical velocity indicates that the comet's orbit around the Milky Way is significantly tilted relative to the galactic plane. Stars with large vertical velocities tend to belong to what astronomers call the thick disk, a population of older stars that formed earlier in the galaxy's history, when the Milky Way was more turbulent, before it settled into the flatter, more organized structure it has today. Over billions of years, gravitational interactions with passing star clusters, spiral arms, and infalling dwarf galaxies gradually heated the orbits of these early stars, giving them larger vertical excursions above and below the galactic midplane. The thick disk stars tend to have lower abundances of heavy elements, what astronomers call lower metallicity, than the younger stars of the thin disk, because they formed before many generations of stellar nucleosynthesis had enriched the galaxy's interstellar medium with the heavier elements produced in stellar interiors and supernova explosions. Multiple independent analyses converged on an estimated age for 3I/Atlas of somewhere between about 7.6 and 14 billion years, with a Bayesian analysis published in a paper by Shawcroos-Kokoroff and Abraham Loeb, pointing to a median age of around 9.6 billion years, and placing the object's kinematic membership firmly in the galactic thick disk population. An independent study led by Matthew Hopkins estimated an age of between 7.6 and 14 billion years with 68% confidence. If these estimates are correct, 3I/Atlas began its existence, formed in the collapsing disk of gas and dust around some ancient star, when the universe was only 4 or 5 billion years old, roughly a third of its current age. At that time, our sun did not yet exist. The raw material that would eventually become our solar system was still scattered in molecular clouds, waiting for the sequence of events, a supernova shock wave, perhaps, or a density wave in a spiral arm, that would set that material collapsing into what would eventually become everything familiar to us. What happened to this ancient comet? The most likely narrative is one that plays out around countless stars during the formation of planetary systems. Young stars form surrounded by a rotating disk of gas and dust, the protoplanetary disk from which planets eventually accumulate. In the early chaotic stages of that process, small icy bodies form in the cold outer regions of the disk, where temperatures are low enough for volatile ices to condense. Giant planets form and migrate, and as they do, their enormous gravitational influence plays havoc with the orbits of these smaller bodies. Through gravitational interactions, close approaches that give a small icy body a tremendous gravitational kick, countless comets and asteroids are flung out of their home planetary systems at velocities high enough to escape the star's gravity entirely. They become interstellar wanderers, carrying the chemical memory of their birthplace frozen inside them. 3. I/Atlas was likely one of these, ejected from its home system somewhere between 7 and 10 billion years ago. sent tumbling outward at roughly 58 kilometers per second relative to its former star's reference frame. Over the billions of years since, as it drifted through the eye's interstellar medium, it accumulated speed from gravitational encounters with other stars along the way. Each near passage, adding or subtracting a small component of velocity, random walking through the stellar neighborhood of the thick disk. Because it was an old object with a high velocity relative to the local standard of rest, it was statistically more likely to arrive from a direction not aligned with the solar apex, the direction the Sun is moving relative to nearby stars. And indeed, 3I/Atlas came from the southern celestial hemisphere, from a direction opposite the solar apex, making it notable in that regard as well. The solar apex is in the northern hemisphere, and astronomers had expected that the majority of detectable interstellar objects would appear to come from that general direction, simply because the Sun's motion through the galaxy would tend to concentrate detectable ISOs in the forward direction of travel. 3. I/Atlas did not follow that expectation. The I-specific star from which 3I/Atlas originated cannot be identified. At its velocity, the comet could have traveled hundreds of light years in the time since it was ejected, and the star itself, a thick disk star, older and lower in metallicity than our Sun, may well have lived out its full stellar lifetime and ended its existence as a white dwarf, or, in the case of a massive star, as a neutron star or black hole, billions of years before our solar system even formed. The parent star is gone. The planetary system that produced this comet is gone. What remains is the comet itself, a frozen messenger from a vanished world, briefly warmed by our Sun before continuing on its endless journey into the dark. The worst-case scenario. Is this something to fear? The title of tonight's journey asks a question that I want to address carefully and honestly. Is the worst-case scenario already happening? And the answer is one that requires some unpacking, because there are actually several different worst-case scenarios that people have had in mind when asking this question about 3I/Atlas. Let me walk through each one, because the science is genuinely interesting, and because being informed is always better than being vaguely frightened of something you have not examined closely. The most immediate question is the simplest. Is 3I/Atlas going to hit Earth? The answer, confirmed by every major space agency on the planet, is definitively no. NASA, ESA, the Japan Aerospace Exploration Agency, the European Southern Observatory, the International Asteroid Warning Network. All of these organizations tracked 3I/Atlas with extreme precision as it traveled through the solar system. Its closest approach to Earth was on December 19, 2025, at a distance of approximately 270 million kilometers, roughly 1.8 times the distance from the Earth to the Sun. That is not close. That is, in fact, far enough that the comet was not even visible to the naked eye at closest approach. It required a telescope to see. There was never, at any point in the analysis of this comet's trajectory, any indication of any collision risk with Earth. The object came no closer to Earth than the far side of the orbit of Mars. NASA explicitly stated that it did not issue any alerts, warnings, or emergency communications related to 3I/Atlas, because there was nothing to be alarmed about. The second type of worst-case scenario that some people raised was more abstract, the question of planetary defense. Even though 3I/Atlas itself poses no threat, its discovery forced humanity to confront an uncomfortable reality. Our planetary defense systems were designed with a specific type of threat in mind: near-Earth asteroids and comets that originate within our own solar system, that can be tracked years or decades in advance, and that in principle could be deflected with technology similar to NASA's DART mission, which in 2022 successfully altered the orbit of the asteroid Dimorphos by deliberately crashing a spacecraft into it. These are meaningful, important capabilities. But 3. I/Atlas represents a different category of object entirely. Interstellar objects travel much faster than solar system objects. At 58 kilometers per second, hyperbolic excess velocity, 3I/Atlas was moving at roughly twice the speed of the previous fastest interstellar object ever observed. The speed matters enormously for planetary defense, because the kinetic energy of an impacting object scales with the square of its velocity, meaning an object moving twice as fast carries 4 times the kinetic energy for the same mass. Additionally, the hyperbolic, essentially straight-line nature of an interstellar object's trajectory means it gives less warning time than a solar system comet, which would be on an orbit that brings it progressively closer over many orbits. An interstellar object comes in once from outside, and its full speed is available from the moment it crosses the outer solar system. Our current deflection technologies, kinetic impactors, nuclear devices, were not specifically designed with objects this fast in mind. The physics of deflecting an object traveling at interstellar speeds is significantly more challenging than deflecting a typical near-Earth asteroid. The International Asteroid Warning Network made the most of 3I/Atlas in precisely this context. Starting November 27, 2025 and running through January 27, 2026, the IAWN used 3I/Atlas as the centerpiece of a global planetary defense exercise, the largest such exercise ever conducted using an actual live interstellar object as the test case. Rather than simulating a hypothetical threat, agencies from around the world, including NASA, ESA, and others, ran their detection, tracking, and characterization protocols on the real object. They practiced sharing data across national boundaries. They tested how quickly different instruments could be mobilized. They looked for gaps in the existing infrastructure. The exercise was valuable precisely because 3I/Atlas was there, moving through the solar system in a way that was complex and real and couldn't be simplified the way a simulation can. The consensus conclusion was that while 3I/Atlas itself posed zero danger, it served as an invaluable systems test, revealing both the impressive capabilities of the global planetary defense network and the areas where improvement is needed. The third type of worst-case scenario was the most speculative, and I want to address it directly and honestly. A small number of researchers, most prominently Avi Loeb of Harvard, raised the possibility that some interstellar objects might not be natural. The argument goes like this: advanced civilizations, if they exist, might create objects that travel between star systems. These objects might look superficially like natural comets. They might outgas as they warm up near a star. They might have a coma and a tail. But they might also display characteristics that are, strictly speaking, anomalous in ways that natural physics does not easily explain. Loeb has argued consistently that anomalous objects should be investigated rigorously, and that dismissing the possibility of technological origin without thorough examination is bad science. The specific claims that were made about 3I/Atlas in this vein included its trajectory being unusually well aligned with the ecliptic plane, a 0.2% probability according to one paper, its arrival direction being near the origin of the 1977 WOW signal, a 0.6% probability by the same analysis, the unusual nickel without iron spectral pattern, the very high CO2 to water ratio, and the non-gravitational accelerations detected in its trajectory. These were presented by Loeb and colleagues in a paper posted to Archive in July 2025. The response from the broader scientific community was swift and largely critical. Astronomer Chris Lintott described the paper as deeply disappointing. Science communicator Scott Manley and researcher David Kipping both pointed out significant flaws in the statistical analysis, specifically that when you are looking for unusual coincidences in data, you need to account for the number of tests you are running, and doing so dramatically reduces the apparent improbability of the claimed alignments. The overwhelming consensus, as Live Science reported, was that 3I/Atlas is a comet. Efforts by SETI's Breakthrough Listen initiative to search 3I/Atlas for radio technosignatures, using the Green Bank Telescope, the Meerkat Array, the Parkes Telescope, and the Allen Telescope Array, found precisely nothing. No artificial radio emissions were detected at any frequency over multiple observation campaigns. At closest approach, the Green Bank Telescope was sensitive enough to detect transmitters with an effective power of approximately 0.1 watts, less than a mobile phone handset, at the distance of 3I/Atlas. Nothing was there. The comet was quiet. What 3I/Atlas actually is, the scientific community concluded, is what it appeared to be from the beginning. An ancient comet from a distant and vanished star system, carrying the chemical remnants of another world through our solar neighborhood on its endless journey across the galaxy. Its unusual characteristics, the high CO2 to water ratio, the nickel without iron, the retrograde ecliptic alignment, the extraordinary eccentricity, are genuinely scientifically interesting, and understanding them will occupy researchers for years. But they are consistent with natural physical processes, not with anything that requires invoking extraterrestrial technology. The universe is vast enough and varied enough to produce objects that challenge our expectations without needing to appeal to intelligence. The opportunity, what 3I/Atlas taught us. Science, at its best, is not about the answers we expected to find, but about what we learn from the things we did not expect. And 3I/Atlas, for all the headlines it generated, was most profound not in what it was, but in what it revealed. About chemistry, about the galaxy, about our own instruments, about the nature of planetary systems across the Milky Way. The most immediate scientific gift was chemical. For the first time in history, astronomers had the chance to study the gas phase chemistry of a second interstellar comet with instruments that had not been available when 2I/Borisov passed through. The James Webb Space Telescope, which was not yet operational during Borisov's visit, was fully active for 3I/Atlas, and collected infrared spectra of extraordinary precision. The finding of a CO2-dominated coma with a CO2 to water ratio of 7.6 to 1 immediately raises questions that researchers are still working through. Is this ratio characteristic of comets that form in the thick disk of the galaxy, around older, lower metallicity stars? Is it the result of billions of years of radiation processing in interstellar space? Is it evidence of formation close to the CO2 frost line in the parent protoplanetary disk? Each of these explanations has different implications for how different stellar environments produce different kinds of planetary building blocks. The nickel without iron detection adds another layer of intrigue. In solar system comets, nickel and iron are found in roughly equal proportions, because both elements originate from the same silicate mineral structures in cometary dust. The absence of iron while nickel was clearly present suggests either a different mineral chemistry in the comet's nucleus, perhaps reflecting different elemental ratios in the protoplanetary disk where it formed, or some process that selectively depletes iron relative to nickel during the long journey through interstellar space. This is exactly the kind of comparison between what we find in our own solar system's comets and what we find in material from another star system that allows us to understand whether our solar system is typical or unusual. The carbon isotope ratios detected by JWST were also informative. The ratio of carbon-12 to carbon-13 in 3I/Atlas's coma was broadly similar to what you find on Earth. This is actually a significant finding. If the ratio had been dramatically different, it would suggest that the specific nucleosynthetic processes that created the carbon in 3I/Atlas's parent system were very different from those that created our solar system's carbon. The similarity suggests that at some level, the chemistry of carbon-bearing ices in different planetary systems may be more universal than expected, that there is something like a common chemistry across at least part of the galaxy, even if the specific abundance ratios of different molecules vary substantially. The wobbling jets detected by the 2-meter twin telescope on Tenerife, where a team observed the comet across 37 nights from July through September 2025, were another unexpected finding. These jets, streams of material ejected from active regions on the nucleus's surface, showed a peculiar wobbling or oscillating behavior that the researchers attributed to the combination of the comet's rotation and the changing illumination geometry as 3I/Atlas's distance from the Sun decreased. This kind of jet activity is common in solar system comets, but had never before been tracked in an interstellar comet over such an extended observation period, giving astronomers the first extended look at the dynamic surface behavior of a body from another star system. The observations made by spacecraft already operating throughout the solar system also proved their worth in ways that will inform future mission planning. Europa Clipper, NASA's mission to study Jupiter's moon. Europa observed 3I/Atlas from about 102 million miles away. NASA's Psyche spacecraft captured images over an 8-hour period when the comet was approximately 33 million miles away. The Lucy mission to the Trojan asteroids spotted the comet from 240 million miles. These observations demonstrated that the existing fleet of deep space missions can be rapidly repurposed, at least partially, to observe unexpected interstellar visitors when they appear, without requiring a dedicated intercept mission. This is valuable information for planning future responses. But the single biggest practical lesson from 3I/Atlas may be about what we could not do. No spacecraft visited it. No mission was launched to fly alongside it and sample its coma directly. We observed it from a distance, with extraordinary instruments, and we learned a great deal. But the science that could have been done with direct in situ measurements, with instruments that could physically sample the gas and dust coming off the nucleus, that could image the surface at meter-scale resolution, that could measure the magnetic field and plasma environment in detail. That science was not done, because humanity was not ready for it. There was no interstellar intercept mission waiting at a Lagrange point, ready to be directed toward an incoming object. When 3I/Atlas arrived, the window for mounting a spacecraft mission was impossibly short. A discussion at NASA and elsewhere about the feasibility of redirecting the Juno spacecraft, then nearing the end of its extended mission at Jupiter, was ultimately not pursued, in part because of the scientific and operational complexity, and in part because of the ongoing funding constraints that affected NASA's operations throughout 2025. This is where ESA's Comet Interceptor mission becomes particularly relevant. Approved in 2022 and scheduled for launch as a co-passenger with ESA's Aerial Exoplanet mission in 2029, Comet Interceptor is specifically designed to address the problem of short-notice targets. Rather than being launched toward a known destination, Comet Interceptor will be placed in a waiting position at the Sun-Earth Lagrange Point 2, a gravitationally stable location about 1.5 million kilometers from Earth in the anti-solar direction, where it will wait, potentially for years, for a suitable target. When a suitable long-period comet, or ideally an interstellar object, is detected with enough lead time to redirect the spacecraft, Comet Interceptor will be dispatched. The mission consists of 3 spacecraft, a main craft and 2 sub-probes, which will separate as they approach the target and make simultaneous observations from multiple angles, building up a 3-dimensional profile of the object. If an interstellar object similar to 3I/Atlas were detected in 2030 with enough lead time, Comet Interceptor might be able to intercept it, sampling material from another star system for the first time in history. The bigger picture: interstellar objects and what they mean for everything. Zoom out for a moment from 3I/Atlas itself and consider what these interstellar objects taken together are telling us about the galaxy we live in. We have now confirmed 3: Oumuamua, Borisov, and 3I/Atlas. Each was different. Each came from a different place and a different time. Each told a different story about its origins and its journey. And the diversity among just 3 objects has already begun to reshape our understanding of how planetary systems work throughout the Milky Way. Before Oumuamua, interstellar objects were theoretical. After Oumuamua, they were real. But we had one data point, one strange, puzzling object that fit no existing category cleanly. After Borisov, we had 2 data points, and the picture was already richer. The first was asteroid-like, the second clearly cometary. 2 different types from 2 different sources. After 3I/Atlas, we have 3 objects from 3 different stellar populations spanning vastly different ages. Oumuamua from a young thin disk system roughly 1 billion years old. Borisov from an intermediate age system roughly 1.7 to 3.8 billion years old, and 3I/Atlas from an ancient thick disk system potentially 9.6 billion years old. Together, they span nearly the full history of the galactic disk. This diversity has significant implications. It suggests that interstellar objects are not produced exclusively by one kind of stellar system, or at one particular phase of galactic history. They are being ejected continuously throughout the life of the galaxy by stars of all ages and compositions at all phases of their evolution. The interstellar medium is not just gas and dust and radiation. It is also thick with the discarded remnants of countless planetary systems, all drifting on their slow paths through the galaxy, occasionally stumbling through the neighborhood of some other star. Estimates of the population density of interstellar objects suggest this is an enormous inventory. The number of interstellar objects currently within the orbit of Neptune, the most distant major planet, has been estimated at something on the order of 10,000 at any given time. Most of these are far too small and faint to be detected with current technology. The 3 we have seen were detectable because they happened to enter the inner solar system, where they were close enough to our Sun to become active and bright enough to catch the attention of sky surveys. The Vera C. Rubin Observatory, now operational in Chile with its 8.4-meter mirror and 3.2 gigapixel camera, is expected to dramatically increase the detection rate. Various estimates suggest that over the course of its 10-year legacy survey of space and time, the Rubin Observatory might detect anywhere from 5 to 70 interstellar objects per year, depending on the actual population density and size distribution, which remain uncertain. Even at the conservative end of those estimates, the catalog of known interstellar objects could grow from 3 to dozens or hundreds within a decade. What will we learn from a large sample of interstellar objects? The answers could be profound. By comparing the chemical compositions of comets from many different stellar systems, by looking at the ratios of water to carbon dioxide to carbon monoxide, at the isotopic ratios of hydrogen and nitrogen and carbon, at the relative abundances of organic molecules. Astronomers will be able to build a picture of how universal or how variable planetary chemistry is across the Milky Way. The question of whether the chemistry that makes life possible on Earth is common throughout the galaxy, or whether it represents one particular flavor among many possible chemistries, is one of the most important open questions in astrobiology. Interstellar objects bring us samples from those distant planetary systems, not rocks in a lab, not spectral observations made across light years, but actual molecules, actual ices, passing through our solar neighborhood close enough to measure in detail. There is also the question of panspermia, the possibility that life, or the chemical building blocks of life, might be transported from one stellar system to another by these wandering objects. The idea is not mainstream, and there is no evidence that it has happened. But interstellar comets like 3I/Atlas are exactly the kind of objects that would serve as vehicles for panspermia if it were to occur. The discovery of organic molecules, cyanide, water ice, and complex carbon-bearing compounds in 3I/Atlas's coma at minimum confirms that the kind of chemistry associated with life's building blocks is not unique to our solar system. The same molecules exist in material from other stars. Whether any of that material has ever carried anything more complex than amino acid precursors across the space between stars is a question that current science cannot answer. But it is no longer the kind of question that can be dismissed as purely science fiction. Beyond chemistry, these objects carry information about the dynamics of the galaxy itself, about how planetary systems form and evolve, about how gravitational interactions between young planets and smaller bodies generate the population of interstellar wanderers. The age distribution of interstellar objects, as revealed by kinematic analysis, tells us that these ejections have been happening throughout galactic history, not just during some early phase of intense planet formation. The velocity distribution tells us about the typical ejection velocities of comets from their home systems, information that helps constrain models of planetary formation and early solar system dynamics. Every interstellar object is, in a sense, a probe that other planetary systems have sent us, uninvited and unannounced, carrying compressed within its frozen interior a small piece of the story of how planets form in a galaxy that is, after all, over 13 billion years old, and has seen countless stellar generations rise and fall before our Sun ever ignited. 3. I/Atlas after Perihelion, the journey out. Let us follow our comet through its final movements in the solar system, because there is something quietly moving about watching a traveler depart. After reaching its closest point to the Sun, perihelion, on October 29, 2025, at a distance of about 203 million kilometers, 3 I/Atlas began its outbound journey. The Sun's gravity, which had been pulling it inward and accelerating it to 153,000 miles per hour at perihelion, now acted as a brake, decelerating the comet as it climbed back out of the solar gravitational well. But the deceleration was gradual, and the comet's hyperbolic excess velocity, that 58 kilometers per second that it brought with it from interstellar space, was far more than enough to ensure it would escape entirely. The Sun cannot hold it. It can only slow it slightly before releasing it back into the dark. In the weeks following perihelion, the comet passed too close to the Sun as seen from Earth to be observed from the ground. But spacecraft were there. The Parker Solar Probe, designed to study the Sun from close range, was in a position to observe the comet from October 18th through November 5th, 2025. ESA's Solar and Heliospheric Observatory caught a glimpse of it through careful image processing. The Jupiter Icy Moons Explorer, or JUICE, made observations in November 2025 from its unique vantage point closer to the outer solar system. By early December 2025, 3 I/Atlas had moved far enough from the Sun to be visible again from Earth-based telescopes. The Subaru telescope in Hawaii captured striking images on December 13, 2025, clearly showing the comet's tail extending away from the nucleus. On December 19th, the comet reached its closest point to Earth, 270 million kilometers away, 1.8 times the Earth-Sun distance, and astronomers worldwide observed it as intensively as possible through this final observational window. With an apparent brightness of around magnitude 10, it was not visible to the naked eye, but it was well within reach of binoculars and small telescopes for anyone who knew where to look. In the same week, the Breakthrough Listen initiative used the Green Bank Telescope in West Virginia to conduct its most sensitive search for radio technosignatures from the object, less than 24 hours before closest Earth approach. The telescope was sensitive enough at that distance to detect a transmitter with an effective radiated power of about 0.1 watts, roughly the power of a small LED indicator light. No signal was detected. There was nothing there to detect. The comet continued in silence. By early 2026, 3 I/Atlas had faded beyond the reach of most ground-based telescopes. It was heading outward, back into the space between the stars, carrying with it whatever secrets remain undiscovered. Whatever is locked in the frozen interior of its nucleus that the Sun's brief warmth did not manage to unlock. The same ices that were there when it formed, in the early days of some ancient planetary system around some ancient star, will freeze back into stillness as the comet moves beyond the orbit of Jupiter, beyond the orbit of Saturn, into the cold outer reaches where comets spend most of their lives. It will not stop there, of course. Unlike solar system comets, which eventually return, in decades or centuries or millennia, 3 I/Atlas will simply continue outward. Its hyperbolic trajectory guarantees it. Somewhere beyond the heliopause, the boundary where the solar wind finally gives way to the true interstellar medium, it will leave our solar system behind. And then it will resume its long journey through the galaxy at 58 kilometers per second, drifting for another epoch through the interstellar dark. In perhaps 1 billion years, or 10 billion, it may pass close to another star. Perhaps, if that star has planets, if one of those planets has a thin crust of beings who have built radio telescopes and learned to wonder, those beings will look up and find it, just as we did, and they will wonder where it came from. The human response. How the world reacted to 3I/Atlas. There is a particular kind of electricity that moves through the scientific community when something genuinely unprecedented happens. The discovery of 3I/Atlas on July 1st, 2025 produced that electricity in abundance. Within hours of the first reports to the Minor Planet Center, professional astronomers were redirecting telescope time, queuing up for observing windows, and firing off emails to colleagues. Within days, pre-discovery observations had been found in multiple archives. Dozens of telescopes on multiple continents had confirmed the hyperbolic orbit, and the object had received its official designation. The response was, by any measure, extraordinarily rapid and well coordinated. Part of what made this coordination possible was the infrastructure that had been built in the years since Oumuamua's discovery. When Oumuamua appeared in 2017, the community was caught almost completely off guard. There were no established protocols for rapid response to an interstellar object. There was no clear chain of communication, no pre-allocated telescope time, no systematic plan for how to maximize scientific return from what might be a very short observational window. The result was that Oumuamua was already receding rapidly by the time most astronomers became aware of it, and several potential observations that might have resolved key questions, particularly spectroscopic measurements of its coma composition, which was essentially non-existent, were never made. After Oumuamua, the astronomical community began preparing more seriously. Networks were established for rapid communication. Some telescope facilities set aside target of opportunity time that could be allocated on short notice to high-priority objects. The International Asteroid Warning Network developed protocols for coordinating observations of unusual fast-moving objects. When Borisov appeared in 2019, the response was already significantly better. The community had several months to observe it, in part because Borisov was discovered further from the Sun and moved more slowly through the inner solar system, and in part because the response infrastructure was more developed. By the time 3I/Atlas arrived in 2025, the infrastructure was better still, and the community mobilized with impressive speed. The James Webb Space Telescope, the most powerful space telescope ever built, had its first observations of the comet on August 6th, just 5 weeks after discovery. Hubble had already observed it on July 21st. SphereX, TESS, SWIFT, and multiple other space assets were coordinated through NASA's Jet Propulsion Laboratory and the Space Telescope Science Institute. The European Southern Observatory contributed the Very Large Telescope's spectroscopic capabilities. The Nordic Optical Telescope contributed early confirmation of cometary activity. The Canada-France-Hawaii Telescope, the Lowell Discovery Telescope, and dozens of smaller facilities around the world contributed astrometry. Precise position measurements that allowed the trajectory to be determined with ever-increasing accuracy. The public reaction was equally notable. Interstellar objects, it turned out, captivate people in a way that few astronomical discoveries do. There is something immediately graspable and emotionally resonant about the idea of a visitor from another star. Abstract discoveries. Gravitational waves, the first image of a black hole shadow, the detection of exoplanet atmospheres, require explanation before they become vivid. But an interstellar comet is immediately imaginable. Something from elsewhere, passing through our neighborhood, close enough to see through a telescope. It is almost like a story: arrival, passage, departure. And stories are what human beings live on. Social media lit up within hours of the announcement. Astronomers and science communicators explained the significance in real time, correcting misconceptions and amplifying the genuine wonder of the discovery. Amateur astronomers photographed the comet with backyard telescopes as it moved through its brightest phases. The news coverage was extensive and generally accurate, with most outlets correctly emphasizing that the comet posed no threat to Earth, while also conveying the genuine scientific significance of the discovery. There was, inevitably, a fringe of speculation about artificial origin and extraterrestrial technology, fueled in part by Avi Loeb's paper and in part by the simple human tendency to want extraordinary explanations for extraordinary events. But the mainstream coverage did a reasonably good job of contextualizing the scientific consensus. This is a natural comet from another star system, with unusual properties that will take years to fully understand. One of the most interesting dynamics was the role of spacecraft already operating throughout the solar system. NASA's decision to coordinate observations across its entire planetary fleet. Psyche, Lucy, Europa Clipper, Parker Solar Probe, Punch, TESS, Hubble, Webb, Spherix, MAVEN, MRO, and others, represented a kind of improvised concert of observing. Each spacecraft contributed a different piece of the puzzle, from a different angle, at a different wavelength, at a different time. The Europa Clipper, designed to study the icy moon of Jupiter, used its instruments to observe a comet from another star. The Psyche spacecraft, on its way to study a metallic asteroid, captured images of an interstellar visitor. The Mars Reconnaissance Orbiter, designed to map the surface of Mars, photographed a comet passing close to the red planet. Science is often like this: instruments and missions built for one purpose unexpectedly serving another, because the universe is not organized around our plans for it. The response also highlighted some of the structural challenges facing planetary science in the mid-2000s. The ongoing funding uncertainties that affected NASA's operations in late 2025 meant that some potentially valuable observations, including extended high-rise camera observations from the Mars Reconnaissance Orbiter at what was nearly optimal distance, were delayed or compromised by the operational constraints of a government shutdown. The scientific community was justifiably frustrated that bureaucratic and political factors were limiting what could be learned from an unrepeatable cosmic event. These frustrations were expressed publicly and constructively, contributing to a broader conversation about the importance of stable funding for planetary science and planetary defense infrastructure. Internationally, the response demonstrated both the strengths and the limits of scientific collaboration. Data from dozens of observatories in dozens of countries flowed into shared repositories and were rapidly analyzed. Preprints appeared on AR Cursive within days of new observations, allowing the global community to engage with results almost in real time, rather than waiting months for the traditional peer review process. This kind of rapid, open sharing of results represents scientific culture at its best: the recognition that interstellar objects are rare enough, and the observational window short enough that getting results out quickly, even in preliminary form, benefits everyone. Multiple research groups were effectively working in parallel on different aspects of the comet's properties, and the community coordinated well enough that results were largely complementary rather than redundant. Perhaps most consequentially, 3I/Atlas made a permanent impression on the question of mission planning. The fact that no spacecraft was ready to visit it, despite the obvious scientific value of in situ measurements, generated intense discussion about what a dedicated, rapid-response interstellar object mission should look like. The Comet Interceptor mission, already in development, was frequently cited. But Comet Interceptor's design parameters limit the types of targets it can reach. Discussions of more capable future mission concepts, ones with higher velocity change capabilities, ones that could be launched quickly toward a newly discovered object, gained new urgency in the wake of 3I/Atlas's visit. If the universe is going to keep sending us these messages, the argument went, we should work harder to be ready to read them up close. The deep history of comets and the universe they inhabit. To understand why 3I/Atlas matters beyond its immediate scientific results, it helps to understand the deep history of comets, both in our solar system and in the broader cosmic context. Because comets are not just interesting objects in themselves, they are, in a very real sense, the universe's filing system. They preserve, in frozen form, the chemical conditions that prevailed at specific times and places in the history of planetary systems. They are time capsules. And 3I/Atlas, with its estimated age of nearly 10 billion years, is one of the oldest time capsules that has ever passed close enough for human beings to examine. Our solar system is approximately 4.6 billion years old. This is established with extraordinary precision through radiometric dating of meteorites, small pieces of asteroidal material that have fallen to Earth and contain radioactive elements that decay at known rates, allowing their age to be calculated from the ratios of parent-to-daughter isotopes. The oldest solid material ever measured, certain calcium-aluminum-rich inclusions found in primitive meteorites called chondrites, date to 4.567 billion years ago, the very earliest moments of our solar system's formation. These tiny inclusions, typically smaller than a centimeter, are remnants from the cooling cloud of gas and dust that surrounded the young sun, and they preserve conditions from the first million years of our solar system's existence. Comets from the Oort cloud, our solar system's own population of distant icy bodies, are thought to have formed in the early inner solar system, within and around the region where the giant planets were forming, before being gravitationally ejected outward to their current vast distances. This means they too are approximately 4.6 billion years old, and they too preserve chemical conditions from those early days. When astronomers observe solar system comets, particularly long-period comets making their first or nearly first pass through the inner solar system, they are looking at material that has been essentially unchanged since the early solar system, preserved in the deep freeze of the outer solar system for nearly 5 billion years. This is why comet missions like ESA's Rosetta, which orbited and ultimately landed a probe on Comet 67P/Churyumov-Gerasimenko in 2014, were so scientifically valuable, they gave direct access to that ancient material. 3I/Atlas, if the age estimates are correct, is more than twice as old as those solar system comets. It formed when the Milky Way was only about 4 or 5 billion years old, in an era when the galaxy was more actively forming stars, when the interstellar medium was less enriched with heavy elements from stellar nucleosynthesis, when the universe looked and behaved differently from how it does today. The elements from which it formed, the carbon, oxygen, nitrogen, silicon, magnesium, and the rest, were produced in stellar interiors that predated our Sun by billions of years, cooked up in successive generations of massive stars that lived fast and died in supernovae, scattering their enriched material into the interstellar medium to be incorporated into new generations of stars and their planets. 3. I/Atlas's parent star was itself the product of multiple previous generations of stellar evolution. It was a late second or early third generation star in the galaxy's story. This deep temporal context matters for what we can learn from 3 I/Atlas's composition. When JWST found a CO2 to water ratio of 7.6 to 1, one of the possible explanations was that the protoplanetary disk around 3I/Atlas's parent star had a different chemical composition than the disk around our Sun. The parent star was likely a low metallicity star, meaning it had lower abundances of heavy elements relative to hydrogen than our Sun does. This could affect the relative abundances of different ices in the protoplanetary disk, the ratio of CO2 to water, for instance, or the abundance of carbon-bearing versus oxygen-bearing molecules, because the overall carbon to oxygen ratio in the disk depends partly on the metallicity of the parent star. If 3 I/Atlas is indeed telling us about the chemistry of early galaxy, thick disk planetary systems, then it is giving us a window into a kind of planetary chemistry that may be quite different from what is typical in younger, more metal-rich systems like our own. There is also something beautiful and philosophically resonant about the scale of what we are dealing with. Astronomers calculate that there may be something on the order of 10 trillion, that is, 10 to the power of 23, interstellar objects currently in transit between the stars in the Milky Way. That number is so large as to be almost meaningless in everyday terms, but it reflects the enormous productivity of planetary system formation and the enormous timescales involved. Every planetary system that forms ejects vast numbers of small bodies during its early chaotic phases. Over the 13.6 billion-year history of the galaxy, countless stellar generations have done this. The accumulated population of interstellar objects wandering through the galaxy is genuinely cosmic in scale. Think about what it means to live inside that inventory. At any given moment, there are thousands of interstellar objects within the orbit of Neptune, within what we think of as our solar system. They are not ours, of course. They belong to no system. They are transients, passing through. Most of them are far too small and dark to detect with any existing technology. They come in, sweep through, and leave without our ever knowing they were there. The 3 we have seen, Oumuamua, Borisov, 3 I/Atlas, are the ones that happen to be large enough, close enough, and active enough to become visible to our instruments. They are the tip of a very large iceberg, and yet each of them brought something irreplaceable. Oumuamua's unexplained acceleration and unusual shape told us that interstellar objects could be profoundly different from anything in our own solar system, that the diversity of planetary formation across the galaxy might produce materials and structures we had not anticipated. Borisov told us that at least some interstellar objects are recognizably comet-like, chemically similar enough to our own Oort cloud comets that the broad outlines of cometary chemistry may be reasonably universal, even if the specific details vary. And 3 I/Atlas told us that objects formed in the ancient early galaxy, in stellar systems billions of years older than our own, can be fundamentally different in their chemistry. That the CO2 to water ratio, the presence of nickel without iron, the unusual spectral features, reflect conditions in a protoplanetary disk that formed in a different era and from different building blocks. Together, these three objects have begun to sketch the outlines of a new kind of galactic science. Comparative planetary chemistry, done not by sending missions to other star systems, which remains far beyond our technical capability, but by receiving the samples those other systems have sent us. As the Vera C. Rubin Observatory and its successors detect more interstellar objects, the sample size will grow, the patterns will become clearer, and the comparison will become more systematic. We will begin to understand which aspects of our solar system's chemistry are universal and which are peculiar to us. We will begin to understand the full diversity of the galaxy's planetary systems, not just from the spectral signatures of exoplanet atmospheres observed across light years, but from the actual frozen chemistry of their discarded building blocks, delivered to our doorstep by the slow traffic of interstellar wanderers. There is a certain humility that this picture demands. We sometimes talk about our solar system as though it exists in isolation, a self-contained system, separate from the rest of the galaxy. But the evidence of the interstellar objects suggests something different. Our solar system is porous. Objects come in from outside. Objects presumably leave from inside. Our Oort cloud likely ejects objects too, sending them out into the interstellar medium on billion-year journeys to some future star. The solar system is not a closed room. It is more like a permeable membrane, exchanging material with the broader galaxy over cosmic timescales, part of an ongoing conversation between planetary systems that has been going on since the first stars formed. We are not separate from the galaxy. We are embedded in it, breathing it in and breathing it out, even if on timescales so vast that we could never observe the exchange directly without the occasional messenger like 3I/Atlas to reveal it. There is a passage in the scientific literature about 3I/Atlas that captures something of this perspective. The comet is described, in the context of what it tells us about galactic history, as a fossil from the galaxy's dawn, carrying the chemical fingerprints of a star system that may no longer exist. That phrase, a fossil from the galaxy's dawn, is the kind of description that rewards slow thought. Fossils preserve the forms of organisms long vanished. They allow us to reconstruct what life looked like millions or hundreds of millions of years ago, to understand evolution across timescales that dwarf human experience. 3. I/Atlas is a fossil of a different kind, not of a living thing but of a chemical environment, a planetary system, an era of galactic history, and it passed within 270 million kilometers of our planet, close enough to study in real time with our best instruments, before resuming its endless journey. The universe offered us this glimpse, briefly and unrepeatable, and we looked as hard as we could. What remains? The questions we could not answer. Science is a process, not a conclusion. And one of the most honest things we can say about 3I/Atlas is that it left us with almost as many questions as it answered. The window for observation was relatively short. The comet arrived in July 2025, reached perihelion in October, came closest to Earth in December, and was effectively gone from our best instruments by early 2026. In 6 months, we mobilized an extraordinary array of instruments and collected an unprecedented volume of data. And yet, we do not know with certainty how large the nucleus is. The best estimate is somewhere under 1 kilometer in diameter, possibly as small as 440 meters, but the active coma surrounding it made direct measurement difficult even for Hubble. Future interstellar objects may have less active surfaces, making nucleus characterization easier, or they may have more active surfaces, making it even harder. We do not know where the nickel is coming from. The detection of nickel without iron remains an unexplained puzzle that does not fit comfortably into the standard picture of cometary mineral chemistry. More spectroscopic observations might have helped, but the window closed before the question was resolved. We do not know the full chemical profile of the nucleus as opposed to the coma. The coma represents material that has been actively outgassed, the most volatile components of the nucleus's surface. The interior, the frozen bulk of the comet that has preserved its composition for billions of years without sublimating, is inaccessible without direct sampling. This is perhaps the deepest limitation of remote observation. We do not know the parent star. All the kinematic analysis tells us is the galactic population from which 3I/Atlas most likely originated, the thick disk, probably more than 7 billion years ago. The specific star, the specific system, the specific location in the early Milky Way where this comet formed. These are lost to time and the chaos of galactic dynamics. The galaxy does not keep records easily decipherable over billions of years, and we do not know how many more there are. Estimates range widely. The Vera C. Rubin Observatory will begin to constrain those estimates as it detects more interstellar objects over the coming years. But the true population of interstellar objects drifting through our solar neighborhood at any given time. How many are here right now, invisible, too faint or too far or too inactive to detect, remains genuinely unknown. They drift through us unseen, carrying their frozen histories, and we are only just beginning to learn how to see them. A closing thought. There is a particular kind of wonder that comes from learning something that genuinely expands your sense of what the universe is. Not the cheap wonder of the dramatic or the scary, but the deep, quiet wonder that settles in when you realize the universe is stranger and richer and more interconnected than you knew. 3. I/Atlas offers that kind of wonder, and I want to sit with it for a moment before we close. Consider what it means that this comet exists. Somewhere, approximately 9 or 10 billion years ago, the galaxy looked quite different. It was younger, more turbulent. Thick disk stars were forming in great numbers from the raw material of early interstellar clouds. One of those stars, we do not know which one, we cannot know which one, had planets forming around it. In the cold outer regions of that star's protoplanetary disk, ices condensed from gas, and among those ices, a small body took shape. It grew, grain by grain, collision by collision, until it was perhaps a few hundred meters to a kilometer across. A small, icy, frozen object, rich in carbon dioxide and water and organic compounds and the other molecules of early planetary chemistry. At some point during the formation of that planetary system, during the period of gravitational chaos that accompanies the growth and migration of giant planets, this small body was flung outward. A close encounter with a giant planet gave it a tremendous gravitational kick, sending it at 58 kilometers per second out through the outer reaches of its home system, past the equivalent of its home system's Kuiper belt, past the equivalent of its Oort cloud, and into the true interstellar medium. And there it traveled, for 9 or 10 billion years. through the dark between the stars, past other stars, close enough to be deflected slightly by their gravity, but not close enough to be captured, slowly accumulating velocity from these gravitational nudges, moving always through the cold, through the silence, through the cosmic rays and the tenuous gas of the interstellar medium, while the galaxy aged around it, while generations of stars were born and lived and died, while heavy elements accumulated in the interstellar medium from all those stellar generations, while small, third-generation stars like our Sun formed from the enriched material left behind, while planets formed around those stars, while at least one of those planets developed a thin film of chemistry that became life, and from that life emerged creatures who eventually built telescopes and pointed them at the sky and wondered what they were seeing. And then, in July 2025, after all of that, after 9 or 10 billion years of silent travel, a telescope in Chile pointed at a patch of sky near Sagittarius and detected a faint, moving point of light. And the universe revealed that this ancient traveler, this frozen messenger from a vanished world, had arrived in our neighborhood. And for 6 months, we watched it. We talked to it with radio waves and X-rays and infrared light and ultraviolet light and visible light, and it replied with the spectral signatures of its frozen chemistry: carbon dioxide, water vapor, carbon monoxide, carbonyl sulfide, cyanide, nickel, the molecules of another world's early chemistry, speaking to us across the deep time and deep space of a 10 billion year journey. Is the worst-case scenario already happening? In the sense of collision risk, no. Definitively, comfortably, reassuringly, no. In the sense of being shown something sobering about our readiness for the universe's surprises, perhaps a little, yes, but in a way that is ultimately encouraging, because the response to 3I/Atlas was exactly what you would want. Rapid, collaborative, thorough, and honest. In the sense of something profound and irreversible, yes. Because we have now seen 3 interstellar objects pass through our solar system, and there is no going back to a time when we did not know the galaxy was full of these wanderers. The universe has been opened up a little further, and that is not a worst-case scenario. That is how science always works. It shows you that the universe is bigger and stranger and more astonishing than you thought. And then it leaves you with new questions to keep you curious for another night. 3I/Atlas has left us now. It is heading out past the orbit of Saturn, past the orbit of Uranus, into the cold outer solar system, where it will eventually cross the heliopause and re-enter the interstellar medium from which it came. If it could know that we watched it, perhaps it would carry something of that brief moment of connection outward with it. A small piece of human attention, of curiosity, of care, sent into the deep space between the stars. Perhaps not, but we carry something of it forward. A chemical signature, a speed measurement, a trajectory, an age estimate, a name, and that is something. Sleep well tonight, knowing that the universe is very old and very large and full of wonders that we are only just beginning to learn how to see. The comet is gone, but the questions remain, and questions are the best companions for a curious mind drifting toward sleep. Rest now, and we will find another extraordinary thing to wonder at together very soon. If tonight's journey resonated with you, a like on this video makes a genuine difference in helping others find the Science Pillow. And if you have not yet subscribed, please consider joining us. There are many more journeys like this one waiting for you, and the universe, it turns out, has no shortage of extraordinary things to explore. Until next time, sleep well, curious mind. The stars are not going anywhere.